Hi everyone. Welcome back to Dave's Math channel. Haven't made any videos here in a while, but I figured it's high time I did one. So today I think I'm going to talk about a very interesting and important topic, and that's Einstein's most famous equation, probably the most famous equation in science, or at least in physics, equals mc squared. Everybody seems to know this equation. As a matter of fact, this is, I think, the main thing that most people associate with Einstein. Einstein was a really, really brilliant physicist. He didn't just come up with equals mc squared. This is probably his greatest formula, but he also developed the whole theory of relativity, both the special and general relativity. This is just one consequence of that theory. There's many, many more. But I don't want to get into everything Einstein did today. I just want to talk about this one equation. And I learned something interesting when I was studying physics, maybe about 30, 40 years ago. Every bit, like I said, I remember our professor said probably 99% of all people in the world know this equation, but only about 10% of them even know what it means, like E or M or C. But I'm going to explain that. It's not that hard. So here's the equation. And E stands for energy, and M stands for mass. That's like weight, but it's not quite weight because it's how much matter is something. Uh, Pound is usually used as a unit of mass in the English system, but it's really a unit of weight, which is really a unit of force. And there actually is a unit of mass in the English system. It's called slugs. Very few people know about that. But I really, really prefer metric, and the metric unit of mass is a kilogram, which most people associate with weight, but it's really not a unit of weight, it's a unit of mass. I mean, a kilogram on Earth is the same as a kilogram on the moon or anywhere else, even in outer space where there's no gravity, it's weightless. And c is the speed of light, and that is a very, very large number, and we're squaring it, which makes it even larger. When you square a large number, it becomes huge. So anyway, yeah, here's the speed of light. It has an exact value. This value was actually defined in 1983. And you might wonder how you can define a speed like the speed of light. Well, it's really just the units that are defined. These are metric units of length and time. The metric unit of length is a meter, m, and the length metric unit of time is a second, denoted as s. So a meter per second is just a velocity or a speed. And the meter, it was funny because there were two different standards used for a meter and a second until 1983. And then somebody had the brilliant idea, why don't we just use the same standard to define them both? And they did that. And once you've done that, you can define the speed of light. So, I mean, it's based on measurements that people were doing beforehand. It's a very, very precisely known number. So it's approximately 300 million meters per second, or 300,000 kilometers per second. I guess a lot of Americans who you are more familiar with the English system say 186,000 miles a second. That's extremely fast. I mean, that's even hard to imagine. That means that a beam of light could circle the Earth about 7 times, about 7.5 times in 1 second. You may remember this scene from the original Superman movie with Christopher Reeve that came out in 1978. There's a scene where he goes back in time by circling around the Earth. If you look at this picture on the bottom, that's him. He was circling the Earth, and it was really kind of ridiculous what he did. And a lot of people wondered whether this would be physically possible. It wouldn't. As far as we know, we don't even know if time travel is possible. But I remember watching this movie. I've seen it several times. He circles the Earth going clockwise, and since the Earth is rotating counterclockwise, I don't know what was happening. I guess he was dragging the Earth along with him, something like that, which isn't possible. But I guess that was making the Earth spin the opposite direction, which was turning back time. Fun fiction, but no realism in that at all. A lot of people think if you travel faster than light, you could go back in time. That's not true either. As far as we know, nothing can travel faster than the speed of light. There are models of general relativity where time travel in the past is possible, but not by traveling faster than the speed of light, but rather by going through wormholes. But I don't want to go through that. I was just talking about the speed of light, and yeah, and here's a table of metric units. They call them SI units, and There's both the fundamental SI units. These are or SI base units. These are shown on the top left. I think there's seven of them, and every other unit in physics can be derived in terms of these. So, for instance, the metric unit of the derived unit of energy, called a joule. That's actually 1 kilogram meter squared per second squared. So it turns out, when I first saw this equation equals mc squared, I wondered what it really meant because it didn't make sense to square a speed to me. But it turns out that the units work out just right. If you use units of kilograms for mass and meters per second for speed and joules for energy, then if all these units are the SI units, then your units of energy will turn out to be in joules. So you can apply that formula, and I actually did it here. So if you want to know, for instance, how much energy there is in 1 kilogram of matter, a kilogram is about 2.2 pounds. It's about the weight of an average book. So just a book. Imagine turning all the energy of a book and all the matter in a book into energy. According to equals mc squared, that comes out to be, here's the exact figure. I'm not going to read that number off, but it's about um, about 90 quadrillion joules. Quadrillion is a million billion. It's a huge amount of energy. And in more familiar units, it's about 2.5 times 10 to the 10th kilowatt hours. That's about 25 billion kilowatt hours. It's still a huge amount of energy. And just to give you some perspective on that, this is the average energy output per household in different countries. You can see United States is second. I guess Canada's number one, probably because it's further north and they have to burn more energy in the winter just to stay warm. But if you look at like the United States, this was actually 2010. It's probably a little higher now, but in 2010, the average American household was burning about 12,000 kilowatt hours a year. That's just one household. And if you multiply that by the number of households in the United States, I looked this up. There's about 126 million households in the United States. So that works out to be about what 100 about 1.5 times what is it 10 to the 12th, about 1.5 trillion kilowatt hours is the total energy output of the United States. And let's just come back to this formula. So this is the one is 2.25 billion. So that one kilogram of matter wouldn't supply a year's worth of power for the United States. It would you'd need about about maybe 60 or 70 kilograms of matter. That would power the entire USA. So, and you don't need that much matter, even to power the whole country or even the whole world. And to give you some more perspective, this is nuclear energy. This is fission and fusion, and I think the world was really, shockingly aware of the how much power you could get from an atom, from a nucleus of an atom when the atomic bomb was set off in 1945 on Hiroshima. I mean, you know, I think they used like 30 kilograms of uranium. Of course, all the mass wasn't converted to energy. About tenth of a percent of it was. But even that amount of energy, I guess that would have been about 30 grams of energy being converted, or 30 grams of mass being converted to energy. That was enough to destroy Hiroshima. And of course, we have much more powerful. We have hydrogen bombs and fusion. There's two different kinds of nuclear power. There's fission on the left. That's where you split a heavy nucleus like uranium. You bombard it with a neutron, and it splits into two smaller nuclei and releases three neutrons and a lot more energy. And this is a chain reaction. If you get three neutrons once, you just use one. That's how the atomic bomb works. It starts a chain reaction. You have to have a critical mass of uranium to do that, though. And one thing a lot of people don't realize is that, nuclear power plants, there's no danger at all. As a matter of fact, it's impossible to have a nuclear explosion like Hiroshima in a nuclear power plant. I think that's been a big misconception among a lot of people. And I think that's one reason why nuclear power is very unpopular. That's not to say there aren't dangers. I mean, nuclear meltdowns. We've had, three really major ones, I think, or at least two, during the last, I don't know, 60 or 70 years. So there are dangers. I don't want to get into that too much. It's actually much safer than fossil fuels statistically. But then on the right, we have fusion here. And actually, fusion produces about 10 times as much energy per unit mass as fission. Like I said, not all the matter is being converted to energy. For fission, it's about a tenth of a percent. For fusion, it's about 1%. So just think about it. I mean, so I actually did this calculation. I'm going to show you the details, but it turns out that about you need about. Remember, I said there was about maybe 60 or 70 kilograms of matter would power the whole United States for a year. Well, since fission only produces about a 10%, only about a tenth of a percent of the matter gets converted to energy. That means about 60,000 kilograms or 60 tons of uranium 235. And uranium 235 is pretty rare. It's only, I think, 0.7% of all uranium. And there isn't even that much uranium in the world. As a matter of fact, it's estimated that at the rate we're using nuclear power right now, um, at least with the method we're doing it with, the uranium in the world would only last about another 90 years or so. So we are running out of uranium. And um, there are ways you could produce more. There are ways we could get more energy from fission, but I'm much more optimistic about fusion because fusion just comes from well, here they show it with deuterium and tritium. Tritium is very rare and it's hard to produce. It's actually radioactive. It's a radioactive isotope of hydrogen. Deuterium is also pretty rare, but you can produce these things from hydrogen. And there's tons and tons of hydrogen in the world. I mean, hydrogen is 10% of water, and of course, we have the whole ocean here on Earth. So hydrogen's in just great abundance. And like I said, you get even more, a bigger percentage of energy out of hydrogen than you do out of uranium. So I don't think once we get fusion, make that practical form of energy, I don't see any danger of running out of the materials needed to produce it. And like I said, you need about 60 tons of uranium to power the United States. You only need about 6 tons of hydrogen. So, and like I said, there's plenty of hydrogen out there. So this just kind of gives you an idea of how, how much energy you get from matter. And this is a good practical application of that. And unfortunately, we do have both A bombs and H bombs. I hope we never use them. But like every other technology, I think there's good applications and bad applications. So we just need to do the right thing. Anyway, that's my talk on equals MC squared. I hope you enjoyed it, and I'll see you next time.